Hello, I'm Zhou Longyu, a PhD student at Johns Hopkins University. Today, I'm glad to share our work, NetLock, faster centralized lock management using programmable switches. This is a joint work with colleagues at Johns Hopkins University and the University of Michigan. So in this work, we introduce a new mechanism to do lock management to achieve both good performance and flexible policy support. Nowadays, more and more enterprises move their workload to the cloud, which increases the demand of database services normally provided by public cloud providers like Amazon, Microsoft, and Google. Log managers are a critical building block of cloud databases. They are normally used to mediate the access to the resource. Let's take a look at a simple transaction. To begin with, a client needs to acquire the log from the log manager. After he gets the log, he can access the resource and do some read or write. After he finishes, the log then can be released. Recent years, some works about in-memory databases and RDMA networks have largely improved the performance of distributed transactions. As a result, the overhead of dealing with the log manager is becoming a major component for end-to-end performance. So we may wonder, can the log manager be faster? Besides the performance, another important factor for log managers is policy support. With global knowledge, traditional centralized log managers can provide flexible policy support, such as starvation-free, priority, and performance isolation. But they often fall short at the performance and are always bottlenecked at the service capacity. While decentralized log managers can provide better performance, but they cannot efficiently support the policies. The most recent work, DSLR, applied the Lamport's bakery algorithm in an RDMA network, which can avoid the starvation and provide high performance, but it can still not support other policies. So can we have both good performance and flexible policy support? We wonder, what if we replace the log manager server with a programmable switch? Here is a simple comparison between a switch-based log manager and a server-based log manager. We can see a switch can provide much higher throughput compared to a log server, and the switch is even not saturated in this case. That might help us eliminate the bottleneck of centralized approach. So with that, we want our system to have good performance, including high throughput and low latency. And we also wanted to provide flexible policy support. Well, it may seem that these goals can be directly achieved by using high performance switches and a centralized approach. There are two challenges to realize the system. First, the switch has a very limited memory to store the logs. Second, although programmable switches are becoming more and more powerful, the functionalities they can provide are still very limited. Here we show the architecture of our system. NetLock processes log requests with a combination of switch and servers. And the switch only needs to store and process requests on popular logs, while the server will help with the rest of the logs. And NetLock is also incrementally deployable and compatible with existing DCN. Before we talk about how we handle the request, let's first take a look at the packet format. The NetLock request packets are specified by a reserved UDP destination port. And the essential fields for NetLock applications are organized as part of the UDP payload. Here are some essential fields. The action type, which specifies whether the packet is to acquire a log or release a log, and the log ID. And the log mode is used to specify what type of log the client wants. And we have the transaction ID. When a packet comes to the switch pipeline, we will check the log ID and decide what operations to take. For each popular lock, there is a circular queue to store the lock requests, and we use some extra registers to keep the head pointers and the tail pointers. For example, here there are 6 requests queued for lock A, and the head pointer is at 1, and the tail pointer is at 7. To better utilize the registers, we let all the locks share a large queue. And again, we keep some extra registers to store the left boundaries and the right boundaries, which can be modified in the runtime. In this way, each lock can have a queue with a flexible length according to its popularity. Please refer to the paper for more details on how we optimize the memory layout and how we handle the lock requests. There are 3 major policies for NetLock can support, namely starvation freedom, service differentiation with priority, and performance isolation. And here we briefly show how these policies are supported in the switch. We store the requests in a first come, first served queue, which prevents a later request getting processed before an earlier request and avoid starvation. It's always challenging to support priority queues in the switch. So in order to support the differentiation with priority, we store the requests with different priority in separate queues and allocate 1 queue in each stage for 1 priority. And the switch only needs to store the high priority requests, while the low priority requests can be offloaded to the servers. And we also maintain a counter as a rate limiter to enforce a quota for each tenant to achieve performance isolation. Now let's go to the evaluation part. Our testbed includes a 6.5 terabps Tofino switch and 12 servers, each with an 8-core CPU and a 40G NIC. We compare our system with 2 RDMA approaches, DSLR and TRTM. And we also compare our system with a programmable switch solution, NetLock. We use a micro benchmark and a TPCC workload with different contention level to evaluate our performance. Through the evaluation, we want to answer 4 questions. First, how fast can NetLock process lock requests? And the second, we want to see the benefit of NetLock over existing solutions when processing transactions. And also, can NetLock provide flexible policy support? And also NetLock's reaction to the failures. In this talk, we will mention the second one and the third one. Here is a comparison between NetLock and other solutions. The left figure is for lock throughput, and the right figure is for transaction throughput. In both cases, NetLock outperforms other approaches and improves the throughput by up to 18 times compared with DSLR. Then we show the performance isolation. We have 2 tenants. The tenant 1 has 7 clients, and tenant 2 has 3 clients, and all the clients are sending with the same rate. Before we enforce isolation, tenant 1 gets more than 2 times throughput compared with tenant 2. After we enforce isolation, we can see the 2 tenants get similar throughput. So to conclude, NetLock is a centralized lock manager, and it co-designs programmable switches and servers to avoid the limitation of switch memory. The evaluation shows that NetLock can provide high performance and flexible policy support, and the code is open source on GitHub. Thank you. Please feel free to contact us if you have any questions.
Okay, thank you very much for a nice talk. I really apologize, folks. My browser tab crashed that had the presenter bios, and I introduced the second paper instead of the first. So that was obviously NetLock, Fast Centralized Lock Management Using Programmable Switches, presented by Zhulong Yu, who's a second-year PhD student at Hopkins, interested in programmable networks. So I apologize again for the snafu. So we have time for questions. I see a few coming in on the Slack. You can ask them either in Slack, or if you're listening here in Zoom, you can use the Q&A feature there as well. So a first question from Tim Griffin. Can you explain a bit how the policies for these locks are specified?
For policy specified, do you mean by how is the policy implemented in the NetLock switch? If so, yeah, there are mainly three policies we can support. For the starvation freedom, we can naturally support it by using first come, first serve queue, and for the differentiation with priority, we support it by allocate one queue in each stage for one priority, and for the performance isolation, we use a counter to serve as a rate limiter to enforce a quota for each tenant. Yeah, I'm not sure if I answered your question.
It's Tim's question, not mine, but I think maybe the question is, how does the administrator of the system actually specify these policies? Are they changing the P4 code, or is there some management API they can use to specify the policies?
Oh yeah, sure. Currently, the P4 code it doesn't need to be changed. We change the control plan. There are some APIs or some parameters you can change to enforce some process.
Okay, I see Tim is typing, so we might get a follow-up question. But another question from Nadir Kadyrov. Can you tell us a bit about how failures work and about the interplay with routing? So the question has a scenario where a server is connected to two top-of-rack switches, and the failure and the handover of state are reordered with respect to each other. Could that break the lock semantics or cause some other issue?
Oh yeah, basically in our design, only one top-of-rack switch is majorly serve as the log manager for that rack. But if the other top-of-rack switch has the resource to store some logs, it can be a backup switch, log manager for the first one. It only serves when the first top-of-rack switch fails. Otherwise, it will be idle for the log request.
And so how would those two, if one was serving as a backup, how would the two coordinate their state in order to handle failures? Or is that future work?
Yeah, it's actually a future work. We haven't like trained those switches together. Yeah.
Okay. I see a couple of questions being typed in, so I'll give those a couple seconds to come in for one last question. Okay, great. So Anna was going to ask my follow-up. Okay. Anyways, some other comments saying this is a really nice idea. Seems like a really simple abstraction that's ripe for offloading onto the network. And I think the evaluation shows the benefits. So thank you very much.
Yeah.
All right. So yeah, there is an audience asking, what is the scalability of NetLock? Could you explain a little bit about the scalability?
Oh yeah, sure. So in the paper, we focused on the rack scale environment, and we also give some analysis and evaluation results to show that the memory of one switch is actually enough for most of the rack scale workload, and we like naturally use the top of rack switch to serve for the servers in the same rack. Yeah, and in case if we need more memory, in the switch, we can also attach some additional switch to serve as an accelerator for the requests.
Yeah, so I also have some personal questions. So in your paper, it seems that you attach a switch to a server. So it seems that a switch and server, they cooperate with each other to provide this locking service. So is it possible to have multiple switches cooperate with each other to some extent in a distributed way to provide this lock service?
That's actually a very interesting direction to go. Right now we didn't support to using multiple switches simultaneously to handle the log requests. But it's a very interesting direction for future work.